Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Roberta Humphreys and Kris Davidson with us today. Hey, Roberta. Hi, Kris.
Hi.
Hi.
How are you doing today? And where are you located at?
We're in we're in Mendota Heights, Minnesota.
Okay.
A suburb of Minneapolis, St. Paul.
Mm-hmm.
Right across the river, the Mississippi River from St. Paul.
Oh, yes. Yes. I biked across there once. So has summer hit in Minnesota yet?
Oh, yes. Breaking all records, at least for early June, with 10 days above 90 degrees and a couple hitting 100, which I realize isn't unusual in Arizona, but it's a bit unusual for Minnesota, at least in June. So
Indeed, indeed. Is humidity there, or is it it's kind of a dry?
It really hasn't been that bad. I mean, it certainly is more humidity than you're used to, but no, it hasn't. The days have not been that bad.
Okay.
Hot, but not unbearable.
So it is June 15th, 2021 here, and it'll be about 43, 44 C, about 119 today in Phoenix. Nice and toasty.
Do you go outside often?
I do. I don't mind the heat. I do go out. I will go out and do my swim, or you don't spend hours out there, you know, without any sort of evaporative cooling going on or something like that. But yeah, I will go out. I will go out. Yeah, so I do it. You have some pretty awesome Egyptian-looking weebles over your fireplace there. Is that what those are?
Yes, we have a collection of Egyptian gods. Some are more formal looking than others. Most of them are kind of clever little takeoffs on what they think the god or goddess might have looked like.
All right, we're going to get a close-up. There is an Egyptian weeble. That is
Advertising. You hold it, Roberta. You don't have
little Egyptians.
The cameras.
Oh, pictures up there. There you go. Hey, little Egyptian. I think that's the goddess Isis.
Isis.
Rather informal pose.
Isis is looking charming with those big green eyes.
Because one of my loves is has always been archaeology, particularly Egyptology.
Okay. Have you been to Egypt?
If I hadn't become an astronomer, I would have become an archaeologist. So here's the remnant of those interests on our shelf.
Have you called Egyptians, and we discovered them at the Oriental Institute in Chicago.
Oh, okay.
Respectable a venue as you can have.
Very cool. Very cool. So have you been to Egypt?
No, probably I suspect.
Bucket. Okay. Okay. Very cool.
Not the way things are going in the world anyway.
Probably not for a little bit.
Yeah.
Roberta, Kris, what do you like to do for research?
Well, in my case, it's been mostly big stars, massive stars. I also have done research in galactic structure, stellar populations, but I guess I'm probably best known for my work on massive stars, particularly what we call the upper HR diagram, and evolved massive stars, you know, stars that are losing a lot of mass, stars that are changing. And that's one thing people don't realize, that these stars actually change in a human lifetime. You actually see, it's not really evolution so much, it's really variations in their mass loss, variations in the wind that change their actual appearance. And that's what I've been focusing on, I think, in the last several years. Kris is more of the analytical type than I am. I'm the observer. I'm the person that goes to the telescope.
Well, that's a partnership.
Person that goes to the telescope. We don't do that anymore. In the good old days, I actually looked through telescopes.
Right, right.
Kris is more the theorist type, more in your line of work, I think.
I think you've got a fantastic partnership there. You've got both sides, or two sides of the coin anyway, or two sides of the.
Yeah, I have to often ask you about the physics.
Very cool. Very cool. And that, I believe, is going to take us into this very lovely AJ article on the mass loss history of red hypergiant VY Canis Majoris, CMA. And Roberta and Kris, take us away.
Well, VY Canis Majoris one of the largest stars known, one of the most luminous known red supergiants, and it happens to be my favorite star. I got my first observation of VY Canis Majoris during my first trip to Saratoga. Rather a long time ago. It was a very low resolution photographic spectrum.
Yeah.
And so I keep coming back to VY Canis Majoris. The neat thing about that spectrum, that first spectrum, I had taken a spectrum in the blue and one in the red. And in the red, there were these two very strong emission lines, now recognized as due to potassium-1. Now, the strongest emission lines in the spectrum of this star, forget hydrogen. This is potassium-1, the strongest emission line. And those lines had been previously observed and identified only a few years before by George Wallerstein.
Okay.
I wrote a little short research note on it back in those days for the PASP and showing the spectrum and confirming what George Wallerstein had said. And as a result, I actually met George Wallerstein only a year or so after that. And so, as we know, George recently passed away. So when I gave the plenary talk last week to the AAS, I dedicated the discussion of VY Canis Majoris to the memory of George. So that's why I say it was one of his favorite stars, and it is my favorite star. And I think that one of the most impressive things about VY Canis Majoris is you can clearly see the record of its high mass loss events in its famous VY Hubble Space Telescope image. Now,
Let me go to the image.
How do I go to that? Oh, I just scanned down there. Okay, there it is.
You tell me to do it. I'm driving. You tell me where to
You're driving. Okay, yeah, zoom in on that figure 1.
How's that?
Not the complete image. I mean, this is actually a zoomed image just on the innermost couple of seconds around the star. The image I often show in publications and talks gets the full 5 arc second nebula. Okay. When you first look at it, you see these very prominent giant arcs way out, several arc seconds from the central star. When you zoom in like this is the Hubble multi-wavelength image. When you zoom in like this, unfortunately the resolution's not that great, but you can see numerous small arcs and knots quite close to the star.
Yep.
And
there.
The record of its high mass loss episodes is staring you in the face. You can't miss it. This star's been pumping it out, and obviously in discrete ejections. You can see those giant arcs. I mean, this is not some spherical outflow by any means.
Nope.
The star is throwing stuff off in different directions. We got our first effort to really kind of measure those motions of the knots came when we got a second epoch of Hubble images. We'd gotten one epoch in '99, then we came back in 2005, got a second epoch, and that allowed us to measure basically the proper motions.
Let me interject background comment. When you see the full image, especially on some of the early HST pictures, what Roberta just called arcs really look like solar prominences. Now imagine a star
giant solar prominence.
1,500 times the radius of the sun, ejects material. When you see a loop prominence, you think magnetic fields. These are they probably really are fossilized prominences. You can just see one to the upper right fairly well in this picture. And they're a few hundred years old. But the point is, really important, there's nothing spherically symmetric about this phenomenon at all.
Yep.
This star is doing like the sun, it's blasting flares off in particular directions. And Roberta's talking about the inner part.
Okay.
Yeah, those giant arcs that you see in the full image, there's really 3 of them. One we call the northwest arc, and then there's kind of arcs 1 and 2 to the south. Those are based on the motions we did, the proper motions we measured with the 2 epoch Hubble images. We also had Doppler velocities from some earlier data a couple years earlier we'd gotten with Keck. Now, those were ground-based spectra. The slit was placed over different parts of the nebula. We were able to measure the Doppler velocities relative to the star. Now, we used the potassium-1 emission line for that.
Oh, okay.
Okay, I said, forget hydrogen here, okay? That's the strongest lines, and they're actually formed by resonant scattering out in the ejecta. And they're very, very strong, and in fact, potassium-1, VY Canis Majoris has the strongest potassium-1 emission than any star. As I said, it dominates the spectrum of VY. So we use their lines, their Doppler velocities, measured relative to the velocity of the potassium-1 emission on the star. So we had gotten Keck spectra, but of course we were limited by ground-based spectra by resolution. Those were adequate for us to measure the velocities of these more prominent outer arcs. And so with that combined data set, proper motions or transverse velocities with radial velocities from the spectra, you get the total space motion of the star, of the ejecta. You can determine, of course, the direction of the outflow. In fact, that's obvious to you from even looking at the picture practically. And you can get the orientation with respect to the plane of the sky. And of course, then determine the time since the arc or not was ejected. Now, the orientation with respect to the plane of the sky was really rather interesting. Not surprisingly, most of the visible ejecta you see is obviously in front because you can see there's a fairly high amount of diffuse ejecta around there. So most of the things you see are kind of projected in front of the plane of the sky. But the northwest arc, which you can see right here, right here, this prominent arc right here, was actually projected just somewhat behind the plane of the sky. So it's like it's moving away from us. Okay. And it, like its shape implied, it was moving in that direction and away from the plane of the sky. Two other prominent arcs towards the front of the nebula, arcs 1 and 2, were projected towards us. Now, these arcs all had ages between 400 and 800 years. So, so we're seeing a record of high mass loss events over the last few hundred years. Now, these inner knots and little arcs you see close to the star, well, we were able to get some data on them, some results on them with the Keck data. But as you can see, that they were just too close to the star and they're individual little knots. So they weren't resolved with the ground-based spectrum. So that's why beginning in 2018, we got these HST STIS spectra, you see represented here by the slits. There were two visits were required with different orientations for the slits. We were going after small little condensations, very, very close to the star, within about half an arc second. And these slits are only 1/10 of an arc second wide. For these knots and clumps of knots down to the south and southwest of the star, we used a slightly larger, wider slit because they were more diffuse, more irregularly shaped, and I even knew from some of their motions that they were moving in certain directions. So we use a slightly wider slit.
Okay.
So that's sort of that's the data. So we have these spectra that we obtained in 2 wavelength regions, one specifically selected for the potassium-1 lines, around 7,700 angstroms, and another further to the red around 8,500 angstroms, where you can see the very famous calcium-2 triplet, plus a number of iron-1, titanium-1 lines that we can measure that they're seeing in absorption. So you can get the absorption line velocities as well as the potassium emission. But it's really the potassium emission that tells the story about the ejecta.
By the way, we forgot to put something about the picture in context, and that is the scale size of this is a few thousand AU. Think sort of the size of the Oort cloud. And the inner part is where those knots are is, 100 AU, more or less a little bigger than the solar system.
These little knots right here in close to the star, they're all at about 300 to 400 AU from the star.
Okay, thanks.
The star itself is pretty titanic. It has, its luminosity is about 300,000 solar luminosities. And we're going to come to Betelgeuse later. So think 6 times the luminosity of Betelgeuse.
Okay.
but only about twice the mass. So the material on it is loosely bound.
Yes. Okay, good.
So,
Thank
so that's basically the observational data. Can we zoom out on the paper a little bit?
we.
I'm not going to spend a lot of time. We've talked a little bit about the spectrum on the star itself and so on, but let's zoom out some more on the paper. Yeah.
You don't hear all that much about potassium-1 in astronomy because if you know a little atomic physics, you'll know it's awfully easy to ionize potassium. And that means that if there's a bunch of potassium-1 here, that is really cool stuff.
Okay. Yeah. So let's keep zooming out. I want to show a little bit more about the results. I'm not going to talk about the central star. It's, it's interesting. Okay. Actually, some of the results that are very relevant to our interpretation in this paper were presented in an earlier paper that Napje letter that came out in 2019. And now I'm going to ask you to go back to that figure again. I'm sorry.
It's all good. It's all good. It's all
the
good.
first paper we wrote on it was about figure 1. Yeah, was about figure 1. Yeah, that's figure 3.
Back to figure 1.
Figure 1. Yeah.
Okay.
Talking about those little knots very close to the star. Okay. When we got the spectra, and I did the extractions.
Yep.
I was very shocked by what I saw, because for decades we'd always seen these strong potassium-1 lines on the star itself. Because bear in mind, I had a slit that went right across the star, as well as these that you see here. There's one right across the star. So I looked at the spectrum on the star.
Okay.
Potassium-1 emission lines were very weak. Looked at the spectra on these knots to the west of the star, and the potassium lines were very strong. In fact, the strong potassium-1 lines we'd always attributed basically to the star and its immediate circumstellar envelope around the star where we thought they were forming. No, they weren't coming from the star. They were coming from these knots, the knots A and B and the W1 slit and W2. And in addition, that's where the strong potassium-1 emission is coming. Another discovery in the first paper we wrote was that there was very strong molecular emission in the spectra from these knots just to the west of the star, particularly a very unusually strong and peculiarly shaped emission band from titanium oxide.
Interesting.
So consequently, my co-author on the paper, helping with identification of that and other molecular emission features, was Lucy Girish, who you probably know from U of A, who does laboratory molecular spectroscopy. So she helped with that, and give her full credit for that. So this peculiar thing, and this is relevant to our interpretation here in this second paper, was that how to explain the excitation of the potassium-1 lines and those molecular features as well. We finally had to, in fact, that was the conclusion of the paper, was we finally had to conclude that these knots to the west of the star had a basically clear line of sight to the star.
Okay.
So there was a hole in the presumed obscuring circumstellar shell that people had always assumed around this star. Oh, by the way, I should have mentioned earlier, it's a powerful infrared and laser source.
Yeah.
There's several magnitudes of circumstellar extinction in front of VY Canis Majoris, okay? But we were stuck with concluding, not looking towards those knots, there wasn't, that there was at least holes or gaps in that presumed uniform circumstellar envelope around the central star.
Okay.
So that immediately, of course, is getting us to thinking, okay, things are different here. Things are more dynamic maybe than we had previously thought.
Indeed. Okay.
Okay, so let's kind of just jump to figure 4.
Figure 4.
Okay. Oh, this shows the details of the slits, where they were going. And now you can see in these images, the individual knots and clumps of knots. You see how complex it is. And This is where you can see where the three different slits were located. So this kind of gives one perspective. In addition to the earlier work on the slits to the east and west of the star, now we're looking south and southwest of the star, the individual knots. So now we're getting their velocities. Looking back again at the previous paper, we were, of course, measuring the velocities of those knots to the east and west of the star. We were getting there. I had to go back in and measure their transverse velocities because in our earlier work, we hadn't done them because they were so close to the star. But I went back and measured them, got their proper motions and got their ages, which were interestingly put most of them within the late 19th and early 20th century. So they were recent ejecta.
Yeah.
Those little knots very close to the star.
The older ones in the picture are mostly hundreds of years old.
Well, these knots here to the south and southwest of the star, when we finish with our measurements and analysis of them, we get ages, of course, not too surprising, a little bit older and more in the 150, 200, 250 year ages.
Okay.
So that was one of the main things, was to measure the ages of the ejecta, their orientation, their motions. And just let's go ahead and I'll show you what the actual data look like. That's figures 5 and 6.
Okay, let's go to figure 5.
On the next page. Okay. I don't know if you can see it very well or not. Maybe zoom in on figure 5 a bit. Can we?
We will do that.
Okay, that's fine. Now these are the actual two-dimensional slits.
Yep.
There's the two lines of potassium 1. I should have mentioned earlier, it's a doublet. Okay, and these numbers that you see here, these are different slits, S1, S2, S3, the 3 slits to the south. And those numbers considered are basically rows in the spectrum, and that's where we did the extractions. And if you look carefully, I think this one's the best example. You can see resolved here with the stiff spectra, so we're looking at resolution of about 0.05 arc seconds, okay? And you can see the individual knots, and you can even see how they wiggle a little bit. And that shows you their different Doppler velocities. So it's kind of staring at you right there in front of you. And again, you see some faint nebulosity down here. There's 2 or 3 little knots here. And you see a nice wiggle up here. Yep. And so that gives you some idea that the motions we're measuring are real. Okay, you can see them right there on the spectra.
That's lovely.
So let's, the next figure 6, is kind of boring in a sense, I guess, because it just shows the actual line profiles. And mainly, and the dotted line basically shows the velocity of the star, measured on the star, compared with the velocity we're measuring here in the individual knots. And you can see there, again, a little bit of the motion back and forth between the different knots. And different knots have, like some of them even show evidence for more complex structure, maybe multiple peaks and so on in some of them. So it's a kind of a complicated picture. But the bottom line, and there's a rather long table in the paper going into all this, the bottom line was measuring the direction of motion, their orientation with respect to the plane of the sky, our line of sight, and of course the ejection ages. And so I really kind of want to concentrate on basically was the results of the paper is the light curve.
And there's that lovely
the crux of the paper that's
mentioned there.
But that's figure 9.
And
we can come back and talk about some of these other strange things later.
Figure 9.
Historical light curves.
These are historical light curves taken from the work by Leif Robinson. He was an editor of Sky and Telescope.
Yeah, years ago.
Many years ago, back in the 70s or something. But these are a couple little research notes he wrote. And well, I'm always amazed by the work that people did 100, 200 years ago. Yeah. You know, it just, I mean, Kris and I have worked on Eta Carina. His famous giant eruption, 1840s, right? And believe it or not, we have a light curve. Those astronomers' visual eye observations, and they did a very good job. They did very accurate measurements. And so if you go back and you read Leif Robinson's papers, he documents quite, in two different research notes, he documents quite accurately on this upper one here. Let me bring it in a little bit more, the upper panel there, okay. He documents quite well, where he found the measurements recorded in the literature and so on. And these are visual, so these are by eye estimates of the magnitudes of the star, okay? So here's the upper panel is basically the 19th century. And one of the things I noticed very quickly is that the ages of some of these individual knots correlated with a time when VY Canis Majoris was showing considerable variability.
Okay.
So it looks like these ejecta had something to do with the minima in the light curve. And one of the things that look where VY Canis Majoris was in 1800 and through actually the first half of the 19th century. It was marginally naked eye.
Yeah.
It's not naked eye now. It was about being measured around 6.5 visual. Today it's 8 to 8.5.
Right.
Yep. 2 magnitudes fainter. Well, obviously something happened. And what happened is you see right here. Now the data is incomplete, okay?
Interesting.
After all, I'd have to live with what we got back then. But obviously some astronomers, amateur astronomers, even professionals noticed something was happening to it. So they got more observations, more measurements from about 1870 to 1880 or so. But what we're really seeing here, if you plot this on a bigger scale, is that there were at least 3 minima, deep minima, when the star faded by a magnitude to a magnitude and a half. And after each of those events, it returned to its previous brightness.
Okay, so bang, bang.
Okay, so that's what we see going on in the 19th century. But look, already by the early 20th century, something's happened. Something's happened. The star got fainter.
Yep.
We'll come back to that. So you, of course, first guess is, formed dust, right? Well, okay, we'll talk about how it did that, okay?
Okay.
Now we progress to the 20th century, and now we're looking at blue magnitudes, photographic magnitudes, not visual. And these are measurements that Robinson apparently made from the Harvard plate collection.
Okay.
Famous Harvard plate collection. Right. So those are photographic. You can see some variability, but look at this. Beginning in the around 1925, the star goes through several major variations, minima. I count at least 7, maybe some smaller, lesser ones as well. And again, what we find measuring the ages of these knots and clumps of knots is that they correlate with, given as well as we can measure their ages, with this 20-year period of considerable activity or variability. And you see these deep minima.
And the combination of the steady left side suddenly lapsing into instability. Intriguing from the point of view of any kind of physics.
Yeah.
Pretty steady for a while, and then suddenly everything fell apart.
Wow. Okay.
Unfortunately, VY Canis Majoris isn't in the current online DASH database that you can access from Harvard. They've measured the plates, but it's taking them a while longer to bring that data online. I actually got in touch with them about it, and I think they're going to send me the data because I want to see. I mean, this is Leif Robinson measuring the plates himself, and I think he did. It looks like an excellent job, but it'd be very interesting to see what they come out with. I'm sure they'll verify the same deep minima. So again, let's move forward here to the bottom panel. Okay, this is again visual. We're back to visual observations now.
Can't see the dates.
Oh, can you move that up a little bit?
Okay.
There we go. Okay. All right, good. So this is now from the AVSO.
Okay.
So these visual measurements, and you see, actually, you see quite a bit of variability, and I kind of think I need somebody to talk to at the AVSO to go through these and just pick out the, you know, the best measurements. But you see here, beginning around 1985 through about 1995, 2000,
Yeah.
1, 2, 3 minima, deep minima. And again, it flattens out again afterwards, okay?
Yep.
Now, when I'm talking about this inner knot, this was kind of it's not one of the visible knots that you see in the images. It's a knot or a spot of strong potassium-1 emission on the slit that included the star. And it's only about 0.05 arc seconds away from the star, but it's clearly a separate spot of potassium-1 emission. And it has to be within the star's dust formation zone. It's probably about only 60 AU from the star. I estimated that distance from the star. So we think it is another knot of emission, but perhaps a more recent ejecta. And so just kind of assuming it has the same outflow velocity as the other knots that are close to the star, we get an age for it that correlates with these two minima. With these minima. So it's something more recent and probably the most recent ejecta that the stars have. Now you notice we don't have an ejecta. We can zoom out on the image on figure 9 a bit. You can see that we don't have, keep going out on there-ish. It's kind of show all of them. We don't have a correlation of a knot with every single dip, of course, in the light curve.
Right.
Not too surprising because bear in mind, we're only seeing we're only seeing the stuff in front of us. Not the stuff that may be behind a lot of obscuring material. So, you know, we're not seeing everything that the star may have ejected. And by the way, this thing called clump C, that's not an optical knot at all. That's one of these knots seen by the ALMA maser observations. Okay, and the ALMA images show several they're very highly obscured. You don't see them in the optical HSD images at all. They're totally obscured. They're very red. And they're off to the east side of the star. And there's sort of like a little arc of 3 or 4 of these small knots just almost right next to the star on the east side, while the ones I was seeing and measuring with Hubble were on the west side.
Yep. Okay.
But that's
this
clump
whole
C.
narrative. Everyone's supposed to be thinking Betelgeuse. If
Well,
you remember the news story about Betelgeuse last year,
Yep.
just remember that story through this whole story here.
Okay. Yes.
okay. So so that was, I think, the main result was finding this correlation of these knots with these deep minima, these active periods in the history of VY Canis Majoris.
Okay.
So the immediate thing is, okay, what's going on? Well, over many years of writing about VY Canis Majoris, we had going all the way back even around the first, easily 10, 15 years ago, when we first got the images. We immediately began thinking about, well, this certainly looks like discrete ejecta.
Yep.
They have to be coming from different regions on the surface of the star because of their direction of motion and their projection with respect to the plane of our line of sight. They're coming from different regions on the star. Now, we already knew at that time, even from Betelgeuse, about the presence of large dynamical instabilities on the surface of Betelgeuse. Remember the spots on Betelgeuse. They don't really look like spots, but you can see variations of brightness on the surface of Betelgeuse. So the obvious thing was to suspect that in this much more luminous, more massive red hypergiant VY Canis Majoris, that what we're witnessing here is the results of surface activity. Large scale surface activity, not just simply minor convection, but maybe something on the scale of like giant coronal mass ejections.
Right.
So that's kind of what we're thinking.
Very
And then we make this discovery and we think, aha, so what's causing the dimming? What's causing the minimum? Well, the most likely explanation, given the nature of VY Canis Majoris, is that this is being caused by dust formation.
Okay.
Individual dimming, okay, individual events that you see here, probably corresponding to the ejection of a gaseous outflow, maybe we should call them that instead of knots, clumps or something, but gaseous outflows. And no, remember that they're coming from different regions on the star and moving in different directions. So you have this gaseous outflow ejected, you know, basically towards us, but over a period of time, probably a few months or so, it moves out of our line of sight.
Okay.
Well, first of all, it probably at a certain distance from the star, 100 to 200 AU, it's going to form dust. That's the dust formation zone. And then as it moves away out of our line of sight, the star recovers back to its former brightness. Notice how almost every one of these, it seems to go back to close to where it was before. Yeah, it's not a big oscillation like you see in a semi-regular variable or a pulsating variable.
Mm-hmm.
Something that looks a bit different. So our suggestion is that what we're witnessing here is dust formation. And I think, remember I said, I think they move out of our line of sight and then the star returns to its former brightness.
Right.
Except when it didn't. Right here, around 1880, 1890, something happened and the star did get fainter and it has stayed fainter.
Yes. Mm-hmm.
So most likely explanation is one of those gaseous outflows, ejections, was nearly in our line of sight.
Mm-hmm.
I know that's a bit hand-wavy, but you know, it's the best explanation.
It's plausible. Yeah, I'm with you. Mm-hmm.
Nearly in our line of sight.
Is if the star became cooler.
Uh-huh. Right.
No, that's a
expanded.
Yeah, that's a possibility.
By the way, the radius of this thing is about 8 AU or something of that order.
Yes.
Smaller than the orbit of Saturn and bigger than the orbit of Jupiter.
Yes.
Okay, this thing is big. It's very big. The reason I think that it's dust formation, basically along a line of sight, remember that problem we had with those knots that were in those narrow slits very close to the star?
Yes.
We had to conclude that they had a clear line of sight to the star
Mm-hmm.
to explain the excitation of the molecules and the lines.
Okay.
Well, one possibility is that the star is indeed obscured by dust, but selectively in different directions. So you have basically various directions with respect to the star. You have nearly a clear line of sight. Now, those knots that were very close to the star with those strong potassium 1 lines,
okay,
yeah, they've got a clear line of sight. But there's other evidence that some of the other knots have to have nearly a clear line of sight to the star as well. And that includes some of what we call infrared bright ones that were very bright in the infrared and basically modeling their infrared emission. They've got to be getting more radiation from the star than some of the other knots are getting. So again, selective directions where the knots are getting more radiation from the star than other ones are. So suggesting that this obscuring material around VY Canis Majoris is definitely clumping.
Yep, and this is not something you'd actually expect because the time scales don't make sense. You eject some material, the star changes, then the stuff comes in between it. That's what ought to happen logically. But apparently it doesn't. Once a blob has been ejected, the path of that star stays clear for many years, which is just crazy. But it's hard to think of any other explanation.
Well, of course, I mean, after we noticed all this about VY Canis Majoris, the obvious comparison was with Betelgeuse. We all know, I think, remember how a year ago, a year and a half ago now, this remarkable unexpected dimming of Betelgeuse by 1.5 magnitudes. Okay, the work that Andre Dupre did with Stiff's UV spectra from Stiff's on Betelgeuse showed that a few months before, and it was before the dimming,
yes,
she was able to confirm a gaseous outflow occurred, which she observed in the magnesium 2 lines in the UV.
Mm-hmm.
And so there was this gaseous outflow a month or 2 before they began noticing the dimming of Betelgeuse. So I think the analogy between VY Canis Majoris and Betelgeuse is quite apparent. Both stars are doing similar things. Both stars having massive gaseous outflows. In the case of Betelgeuse, it's obviously more extreme. You've got a much more massive, more luminous star. Sorry, VY Canis Majoris is the more massive, more luminous star. So it's a more extreme events, more extreme phenomena. And therefore, probably the dimming in Betelgeuse also was due to dust formation, temporary. Because Betelgeuse's dimming only lasted a few weeks. I failed to mention the width of those minima in VY Canis Majoris. Those are like 2 to 3 years. Okay, 2 to 3 years. So, you know, that's significant. Betelgeuse was like, I think we often say VY Canis Majoris like Betelgeuse, but you know, a much grander scale.
Grand Betelgeuse. Yeah, we did a YouTube video with Andrea Dupree talking about this work, and we'll put a link to her video in the description below this one.
Yeah, and one other point I'm going to make. So here you see similar physical phenomena going on an extreme star like VY Canis Majoris, and a more typical red supergiant like Betelgeuse. So we take the step then to suggest that these massive gaseous outflows are probably occur on all red supergiants, and therefore are a major contributor to the mass loss of red supergiants. The mass loss mechanism for red supergiants has been in doubt for a long time. And in the case, we went through the numbers on VY Canis Majoris, not included in this paper, but since I've gone through the numbers, and we can get the masses for some of the small knots and clumps that are bright in the infrared. We can get their masses.
Okay.
And they on the order of greater than the mass of Jupiter.
Okay.
They're the hundredth of a solar mass and up, because what we can do is get sort of a lower limit on the masses from the infrared test.
Nice.
And so if you assume, okay, if they just assume that all those minima in the early part of the 20th century produce a knot with the mass of Jupiter, you come out with a mass loss rate that actually explains the observed mass loss rate for VY Canis Majoris.
Very good.
It just doesn't just dominate it, it explains it, it accounts for it. So this could be a major source of mass loss for red supergiants, one that I think has gone previously unrecognized. So that's one of the major conclusions that we came to as well.
The convective cells on these stars are big. It's not like the sun, where you have almost invisibly small convective cells. On even Betelgeuse, for a long time, it's been recognized each convective zone is big. I mean, you know what I mean.
Cover a significant fraction of the surface.
The big cells. Yeah. And on VY Canis Majoris, they might be almost the radius of a star. I mean, the outer radius. And so you have MHD stuff happening like wild.
All over. Very cool.
So that's our main results on VY Canis Majoris, but it's there's a lot more to its story. It's got a very complicated story, I think.
Well, Roberta and Kris, I want to thank you very much for walking us through your very lovely paper. And let me ask, since you hinted at it several times when you were going through it, where do we go, let's say, over the next 5 years or so? Are there new observations? Is Vera Rubin Observatory going to do something spectacular? Are there additional space telescopes? Are there additional theoretical calculations to be done?
Oh, definitely. Well, as you can imagine, when this paper came out, well, first of all, we got a press release from NASA and the Space Telescope Science Institute. So a lot of people got very interested in VY Canis Majoris. So we're doing a major campaign on it now with Hubble, with the VLT, and we're trying once again to get ALMA time, and there's a good reason to get ALMA time. VY Canis Majoris has a very complex molecular history. It has more molecules in it, atectedins, ejecta, than any other red supergiant, 25, including carbon-based molecules. Okay.
Nice.
So one of the things I'd really like to find out is, and actually Lucy Zurich in one paper she wrote many years ago, found a correlation between different molecules and different outflows, different ejecta. So one of the things that would be really interesting to do is using ALMA with its spatial resolution is basically map the distribution of these molecules in the ejecta. See if they're correlated with different arcs and clumps of knots. And then what could you start thinking about? Has there been dredging? As stuff that, and different molecules even getting ejected in different directions and so on. A very complex chemical history.
There's a funny,
and maybe bring into question what its evolutionary state it really is.
There's a funny social quirk here with very massive stars that are cooler, like Eta Car. It's been very difficult to get theorists to do anything because they're scared of it with good reason. But in this case, we've got cooler stars, which are more complicated and harder, but we've got this vast reserve of people we don't know very well who work on the sun. And they are accustomed to really, really hard problems.
I'll take that as a throwdown of a gauntlet for the theorists to pick this. I'll take it as.
No, but so more work is being done, and we hope we get all this telescope time back for. And if we do, I think you'll be seeing more papers on VY Canis Majoris.
Awesome. It's nice to hear it's with all the work going on, it's got a really bright future, so to speak, even if it dims.
They often said, they always point to Betelgeuse and the nearest star that's likely to go supernova, right?
Yeah.
Well, I think VY Canis Majoris is a lot closer to going supernova than Betelgeuse.
We'll have a race. How about that?
Okay.
Very cool. Roberta, Kris, thank you once again.
Thank you.
Sure.
Thank you, everyone, and we'll see you on the next one. Bye-bye.
All right. Bye. Thank you.